stuff in. The reason I mention that is the midterm, if you were to study prepware for it, might get quite confusing because we haven't covered some of the later classes. So studying prepware before we cover the whole class, not a terrible idea, but it's not necessarily advisable because we haven't covered the material. Once we get to the final exam is more like 60, and I'm going to call it prepware-ish questions again, with about 15 on the end that are Visser type, worth about 20 points. So once you get towards the end, if you wanted to study something, prepware is not a bad idea. As a reminder, you don't want to study your prepware like they teach at Baker, where you're memorizing answers. You want to study prepware so that if you read the answer, you understand the concept. And if you don't understand the concept, go figure out why not. The nice part about prepware is it lists where they got most of the info from. We get in your books and all that stuff. So that's how the schedule is going to get laid out in here for timing, midterms, and such like that. You'll notice there's a video here from, I think it's John King. I don't think Martha makes an appearance here, which is a bit of a bummer. John and Martha spoke on safety yesterday at IAMA. I missed it. Somebody was like, they gotta be like 90. I'm like, well, they don't age anymore. They just. But anyway, so this is a King video review, and you notice I put some timing in because there's some parts he doesn't explain very well. We'll just put it that way. So we'll jump around, but that's this one. More fun is this Thursday. This Thursday you're not gonna miss. A movie called Frozen in Time. It's the story of the Keybird.
Watch that.
What? Who?
Fire class.
The whole movie?
The whole one. Because she was,
I heard there was another one.
It's on my schedule.
It's also crossed off your schedule.
There's another one Nick was mentioning.
Yes, I was wondering about that one too.
That ends better that we could watch.
The point for my class was not in ends better. The whole point was to get you to watch it, and then you get to the end, and the plane burns down.
You destroy it.
I'm
And
not.
it breaks.
And you say it doesn't matter how hard you worked at being a mechanic. You don't do it right, the whole thing burns down. Little mistakes. You run a wire. It's not supported. The zip tie breaks.
And you can also die of crippling pain and internal bleeding.
Yeah, because he overworked himself. Yeah, so overwork is a good thing. You know, Mike Rowe gives, what do they call them, work ethic scholarships? I did fill out somebody's reference the other day. Okay, another movie. Well, you guys might just get more lab time, I guess. Sheesh, that was my movie. She was sick, you said? She doesn't want her class time back for the day she was sick? The fire suppression definitely didn't work. I'm not sure what you learned about fire suppression.
There's more human factors.
Okay. Well, that's a bummer. Okay. Other than that, then, I put on your schedule. You should have the same one, I think. Yeah, where it's got page numbers, and I'm pretty sure I've updated all the page numbers to your current power plant book that you have. That ends with a B, Bravo, right? Ooh, mine's in my office. So you'll notice on the schedule, I did give some page numbers for you to read through, and or that we're covering. I do recommend reading those in this class time. Here is kind of our expected time frame. You'll notice I put the labs up on here, and apparently on this day you'll get extra, because apparently we're not going to rewatch Frozen in Time. What you'll notice on the lab hours to complete estimate that I have on there is some of those are much higher than if you're rushing, you could get done. Now, one of them might be lower. I'm going to have a discussion with my correctly aviation-sized instructor on a thing or two, because I gave him this beautiful highlighted sheet. Did you guys see this in Ryan's class? Never saw it. Okay, I I gave him this beautifully highlighted sheet to show y'all, and I said, hey Ryan, I know you got them taking the wings off the aircraft, and you think they can still get to the cockpit when the wings are off, because they're going to be replacing wires. Well, that's terrible. You'll see it a little bit later. Why is that so terrible? I'd really like you to see that. That's not working. All right, we'll get back to that. It's going to hang on the back of the board. I'll just read some. Cessna 172, 5452 Foxtrot. Right mag P lead, left mag P lead. Start wire from ignition switch. So these are all wires that we're going to want you guys to replace on aircraft. I gave Dean and Hannah and I have a copy of our instructor checkoff. Now a lot of your labs we'll cover in a minute are on Moodle, but on the wire replacement lab 2B that's on your sheet, that's crazy how bad that is. They have a spot for, you do have to make a bonding wire. Now bonding can be made out of insulated wire. That's a weird looking long bonding wire. It can be made out of this heavy thick stuff, right? Bonding wire. There's a bunch of different ways. Your standard bonding wire is gonna be a little bit more like this length. Because it's really so simple as you're just grounding, right, a component. I'm not gonna give you a whole lot of instructions. The main thing with bonding wires is if you test the ohms on a milliohm meter, how many ohms or less do these have to be? 003, which is 3 milliohms or less, right? So one of your labs has you making a bonding wire, that's a check mark. You're gonna do it, you're gonna go to the instructor, they're just gonna ask you that question, how many ohms was it? The next part is wire selected on our sheet. So we're gonna say, okay, they signed up. Now, that one is gonna be easily confirmable because this will be hanging on the back wall and you will put your name next to one of the wires on here and you're gonna say, hey, that's my wire that I'm doing. And I think I have 32, 34 on here. Part of that is I have the Cherokee 140, right mag P lead, left mag P lead. That aircraft got special treatment. It got a little highlight towards the side because the P leads on those go from the ignition switch, mag switch, whatever you want to call it. They go up to the firewall and they go into this little box thing in the firewall and there's kind of like a connection in there. Now I can't remember exactly how the connections go inside. I just remember when some students did it last year, they were really fighting with it because one side gets soldered and the other side does not. So I wrote right on here, will be a challenge, but it's a good learning experience. So if you're up for a challenge and or want to take an aircraft that's outside currently and not have to have an issue with what I'm going to say next, maybe you want a challenge. So everybody gets to do their own wire. Now that said, whoever's doing the right P lead and left P lead on the Cherokee probably would be good if you work together. For instance, there's 2 bolts that go through the firewall, and it's pretty hard to do those on your own. The other part is it's hard to get 4 people in the cockpit of these aircraft laying underneath it, right? So this will go on the back wall. And you know what? Don't put your names down. I don't care. I wouldn't put your name down until I went and physically saw the wire, but I'll pass it around. You'll kind of get an idea of what's going on that sheet. So that one is 2B here on your sheet. 6 hours. 6 hours, Case. Is it really going to take me 6 hours to replace a wire? Well, the idea is pretty much every one of those wires goes through the firewall. So we're not talking a little wire up in the engine compartment. The main objective of this lab is to give you hard work to make curse me. Well, yeah, that's pretty much it. The main objective is wire security. Now we're going to be talking a lot more about wire security. We're going to go back and review stuff like high temperature areas, engine compartments. We're not using cable ties. How do we support them? How often are they labeled? So I'm not just looking to see that a wire connects. Let me back that up. I'm not looking to see that a conductor connects an ignition switch in a magneto. I'm looking to see that the correct wire is run, supported, routed, and labeled correctly, right? So you're putting this wire in the aircraft, and the last thing I want to hear when I'm inspecting this is, that's how I found it, Case. That is the last thing I want to hear. The objective is we are slowly cleaning up our SMAT aircraft. I don't think you guys got the little box I made for Nick yet. I haven't had the instructor meeting yet that says, let's SMATitize our aircraft. Now, historically, what does SMATitize mean? Make it worse, yeah. And I actually learned a term a couple weeks ago called studentize. Studentize, that's been studentized. And that's where at some point SMATitize came from, is they're like, hey, we can turn it to SMATitize. Studentized means we've had 2 decades of students working on this stuff, and it's getting wore out. And then that became SMATitized. Well, we're gonna change the definition of SMATitized. We're gonna change the definition to taking something that wasn't in good shape, and we're gonna bring it back up to good shape. So that's gonna be the goal, and especially with Lab 2B, I would like you to SMATitize the wire that you're installing, which is gonna be, I'm gonna take a resource, I'm gonna improve it so that we can use it for generations to come, all right? So that's six hours. So you're gonna have to find the wire in the wiring diagram. What gauge wire was it supposed to be? Now, if there are things that come up with that one, like, hey, we don't have that gauge wire, or something silly like that, come talk to me, come talk to Dean. We'll discuss what our options are. Maybe the option would be, well, maybe we can put one size bigger wire in. We can talk through that. You know, in a shop, you'd order the right wire, but I think we have almost all the right wire around here. But so you're gonna check in the manual, and we'll review that on, hey, what size wire, how do I put it in, and how that works. So speaking of wire, I went and grabbed the shielded wire. This stuff is a couple dollars a foot. A lot of the wires listed on there are mag wires or P-lead wires, however you want to phrase that. So we can use this. If you go back to, and I think I have it on the slide, it'll show up later, but airframe, which was 161, lecture 7. It has the pictures of how to make the P-lead, you know how it has to go, you have to pull it through and it goes backwards. And so it'll come up on the PowerPoint later if you want to write it down, and I might even just jot it. It is 161 well, let's say 7, I'll correct that if I get it later. You could always look in AC-43, you could always look in the manual of the airplane you're working on. I know the 172, the 97 and on 172, has pictures of the P-leads of how they're supposed to be routed. So, this is the wire. I will end up putting this in this box, and that box will, I think, sit just outside the door. The reason I'm putting it in the box, make sure you all see this fancy box I have. When you take the P-leads off the aircraft, they're 3 foot long, 4 foot long, at a couple dollars a foot. Please return your scrap or old P-leads to the box. That way, next year when everybody does their projects, they don't have to use my several dollar a foot wire times 100 foot. They can just use the sections you just took off the aircraft, and we'll keep cutting them down until they get shorter and shorter, and we got nothing left. That'll be the plan. So return the P-lead that you took off to the box, if it's a good P-lead, and that way we can keep using it. Comments, questions on that lab 2 of you're gonna replace a wire? Oh, yeah, your comment or question here. There's stuff in the cockpit of like 3 aircraft out there. I feel like I planned ahead for this to say. So what, how long's, Tiki said maybe Tuesday. How long is that stuff gonna be in the cockpits? Wednesday? Okay. And then it comes out Wednesday? Is Wednesday like, why Wednesday? Education.
That's when we start putting it back together.
When you start putting it back together? Okay. We'll talk to Ryan. I doubt he'll be in today, because he was in all day yesterday. I might even call him, Monday. Are they all packed up? Like, do you have to do anything else in the cockpits? Okay. I might call him on his day off and be like, did you inspect the cockpits? can I have them pull everything out? Because if you're packed up, I gotta figure that out. So, because 3 of those aircraft, it's gonna be pretty hard to get to that wire. Now, that said, that's a good segue to some of the labs can be done out of order. So maybe you're one of the 6 to 8 people that pick those aircraft. Maybe you want to wait to do the wire until after the stuff comes out of the cockpit. That would be another way to do it. Because actually those are, I don't want to say the easier ones, but they are some of the easier wires because, well, there are decent aircraft, right? And you're going to be back in there doing flight controls, so you're back in that anyway. One of the big things we said with this wire is correct wire, correctly labeled, correctly secured. Well, part of correctly secured means when you work the flight controls, it's not going to hit our wires, right? So that's the kind of stuff we're looking for. So some of you are going to be back in there. If you're one of the teams that's putting together, is the 210 missing its wings? If you're one of the groups that's going to be putting together the 210, hey, maybe picking the 210 to do a wire would be good, because now you're not trying to get in an aircraft somebody else is working on. Oh, so that's part of why I did not assign the wires. I have found it tends to work best to let you guys do it. If you need help assigning them, let me know. Okay. We are going to go through each one of these labs kind of in order. They are up on Moodle, but I print this off to try to make it easy for you. Lab 1 is just Moodle questions. You'll notice I had it on tomorrow today. Same day. So lab 1 would be one you could do today. Lab 2A is a bunch more Moodle questions. That is another one that would theoretically be, you could do it today. The reason I put it out here on Monday was you want to wait on that until after the lectures are over, right? So, well, once we're done lecturing today, that could definitely be worked on today. Hour, 3/4 hour. Lab 2B, we already talked about a lot, 6 hours. Should give you plenty of time, don't rush it. Big part of that one is wire security. We're going to talk about it in labs. I just ordered this stuff. It was it $1 a foot? $1 a foot for this like plastic stuff. I'm going to pass it around the room. It's called Coraseal. I talked to Dale Coates down at MMS, probably the most knowledgeable Cessna 206 mechanic I've ever met. Okay, Dale Coates down at MMS. He did our annual on our float plane, did an amazing job, found a bunch of stuff. Anyway, I was asking him at IAMA, hey, I catch a little grief about zip ties. And he was like, he was even more hardcore than I was. And I was like, yes, because, yes, he is the missions aviation mechanic in my opinion. He is amazing. And he was like, well, do you use Coraseal? And I'm like, well, I talk about it a little. He's like, you should really get him familiar with it. And I was like, okay. So I ordered that. I actually rush shipped it because I ordered it Wednesday. So instead of just talking about it, we're going to try it a little bit. I put a phone call in 3 times to the manufacturer. I'm gonna see if we can get a discount. Because it'd be nice if you get to practice more often on that stuff. And we'll cover how to use it later. Think of it kind of like using a zip tie, right? It just goes around stuff. You can make it a standoff in that, like, say you have even an engine mount, and you have a wire that you got to hold. You'll wrap the Coraseal around like that, like a zillion times, and then tie a knot here, and it does a great job. And you can put it all over the aircraft. It's a little old school, if I can phrase it that way, but it's best school. It's old school, but best school. So anyway, we have that to either use when you do your wires, and or to practice with. We'll tie some knots in, I think it's a later class. The less old school way, and we'll talk about it later, is to go with this type of clamp. So if you have a wire that runs by the engine motor mount, you put this one on the motor mount, and then that'll hold your wire, right? Holds it off. We don't have zip ties, and we will cover this later. I ordered a bunch of the smallest Adele clamps I could find, 1/8-inch ones, to hold wires. We're going to cover this in detail much later. We even got some small ones. That's why I spent several hours 2 weeks ago, if you all saw me, sorting out those Adele clamps. It was to get ready for Lab 2B. We're going to get these wires routed better. All right, Lab 3, starters. You might have saw the pile of starters out there. You all get to pick your own starter out. You will disassemble the starter. Once it's disassembled, there's a sheet that me, Dean, and Hannah have that you'll call us over and say, hey, can we talk about my starter? So it's kind of a check mark of, yup, they got it disassembled, but more to the point is we're gonna ask you some questions about, hey, what's the commutator? A little bit of review on how the starters work. Is this wired in series or parallel? The field versus the armature. My brain just was like, is it still an armature? Anyway, the field versus the rotor. I'll have to review that one because we're not harvesting. But that'll be 3, and then you'll put it back together, and we'll talk a little bit more about it, but you'll test it on the bench. Basically, we'll hook it up to power. There's safe ways to do that, and there's less safe ways to do that. The less safe ways look like jumper cables to a battery without the starter secured, and when they spin, they like to jump off tables. Also, if you do it that way, your clamp biting on the threads of your starter will ruin the threads of our starter. So we're going to talk about how there's better ways to test them than just jumper cables sitting on top of your workbench. But the second part of that is you'll make sure that it runs when you're done. You do not have to paint the starters when you're done. Even though your lab says paint it and clean it up, they're basically painted. This is more of a let's get inside a starter to see what it looks like than it is a rebuild. So if your lab says paint it, if you got a really bad one, don't worry about it. But the starters, you don't have to paint. Okay. Lab 4 is Moodle questions on the U21, the King Air. You're basically going to do a bunch of questions on it and then go inspect the wiring to the starter generator on the King Air and give me a list of things that are wrong, if there's anything wrong on it. I believe the way it's written is you get to, I got to double check, pick the right or the left engine to inspect. I think I left it that way. And then you'll just, but if you do that, and I might have to review how I wrote it. If you do that, make sure you tell me I did the right engine or the left engine, because the wiring's not the same as far as some of the discrepancies I may or may not have written down for the King Air, right? So that'll be the King Air. Lab 5. Moodle questions, kind of, I say Moodle, they're mostly manual questions. They send you a bunch of different manuals to understand starters. Lab 5, you'll notice, is way out here. If you try to do lab 5 before we talk about starter wiring circuits, you're just going to be really confused. So don't try to do lab 5 until after next Thursday at least is my recommendation on lab 5. That's why I got it stuck out there a ways. Lab 6 is alternators. On Moodle, if you're on there, where you're at the PowerPoints, the top PowerPoint is actually a slideshow that shows somebody taking apart an alternator step by step. You can find some manuals for, I think they're AC Delco, alternators. There are a pile of alternators you guys saw out there. You each get to pick your own alternator. Most of them were buried in mud at the scrapyard, which is why they look terrible. They were junk. So for some reason, it's probably not working, right? But you're going to take them apart. You're going to bring them to the sandblaster. You're going to clean them all up in the sandblaster after you take all the components out. You're going to try to figure out, why doesn't this work? We've been doing this for so many years that I have a box, an apple crate, that's got all kinds of alternator parts in it. So if yours, we can tell why it's not working. We can probably find the parts to fix it and get it going. We do have a lecture on alternator operations here this Monday. What date is that? Whatever date that says it is. 3:30. So once we get out to here, it's going to make it a little bit easier to do some troubleshooting and whatnot with alternators and components. But what I would recommend doing is pick your alternator and get some aerocroil. Aero sounds fun like airplanes. All it means is aerosol. Get some croil, get some rust breaker, get some whatever on the bolt and on the shell of it so that it'll come apart. If you pick it today and start soaking it and just hit it once a day for the next 3-4 days, that'll make it easier for you. We'll talk a little more about disassembly. A lot of times the nut on the alternator, you can't get a hold of the pulley very well to get that off. So a lot of times the nut on the alternator, you're going to use an impact, probably the pneumatic impact, and to get that nut off. Back on, you necessarily going for, according to the service manual for this alternator disassembly and reassembly. If you can find one for it, great. We're really going for, you will probably never again in your life go inside an alternator. You're gonna take it off the airplane, you're gonna send it in, or you're just gonna put a new one on. So this is a little bit to train you guys in, hey, what do they look like? Hey, how do I get a nut off that's rusted on? Croil or something like that. But also, how does it work? How do the brushes work? There's a couple tricks on the brushes on them. There's a pinway that we'll cover, I think, this day here. Pretty sure it's that day there. Might be voltage regulation day. So that's that lab. Notice 6 to 8 hours. It doesn't take 6 to 8 to disassemble and reassemble, but once you disassemble, sandblast, now I gotta paint it. Is it a coat or two? Let the paint dry. Now I gotta reassemble it. That's why it's 6 to 8 hours on lab 6, and you notice they're towards the end of class. So you could get started on disassembly. I would recommend open up that PowerPoint and click through a little bit. Maybe today when you get a chance, just to give you an idea of what's going on. Lab 7, alternator troubleshooting. The break coming up after I explain our schedules. We're gonna stop out at the alternator troubleshooting board. I don't think you guys have done any troubleshooting on that, right? Blackboard, really noisy. I think you guys did the generator. I'm trying to remember, I don't think we had you do the alternator yet. So, we'll introduce you to that board. There's 30 of y'all. The lab you have in your hand, I believe, says pick one of 4 faults. Is that what's written on the front page of that? Lab 8? 7? Lab 7? I can find it in my book.
Troubleshoot the fault provided by the instructor, 7, 10, 12, or 14.
7, 10, 12, or 14. So whether you pick it or the instructor provides it, the idea is you pick one. Now, you can do more than one if you want. We're going to explain that system a lot on this day, Tuesday, which is why lab 7 I have way towards the end, is you really don't want to do lab 7 before this Tuesday. Now, you can, if you're feeling confident with electricity and how alternators work. We have 30 people to get through it. We're not all going to get through it on this Wednesday. So this Wednesday, Thursday, and Friday, there's going to be a little bit of a backup at that thing. And you'll also notice provided by the instructor, I would say half of y'all are probably going to want to have me or Dean or Hannah with you when you troubleshoot it. That, or maybe one of your friends that understands the board. It's a little complicated. I will explain it in detail here. So don't freak out. You'll get it in detail here. But starting this day, people are going to be starting on lab 7 through the end. Reminder, these lab numbers are suggested, or maybe a way to phrase it would be, they're a sample of the timing you could use. Rearrange the numbers a little bit, but with some of those exceptions, knowing, hey, when am I going to have the lecture on that? Well, maybe I don't want to do that lab until then. All right, we're getting there. Lab 8, wiring understanding. This is one last time to get you guys to basically wire up a master and a starter contactor on the tabletop. It takes about 2 minutes if you have the components, if you know what you're doing. If you're still struggling, it might take you an hour or 2. Right now, Mike has my little coffee box with the parts in it, and we're gonna hopefully go through that with him. Now, a little bonus, Mike, I hate to say it, but if you look at this lab, right when you're getting ready to explain it to your instructor for the one on your bench, you might get 2 birds with 1 stone. So, there you go. You might kind of, because it's a repeat lab as a review to make sure you all know how these work very, very well. And we're going to cover it a little bit. We're going to review it again in our lecture today, but that's what that is. If you're like, Mike has the bucket and I can't do it yet, when we go out there, the little cabinets, there's a whole stack of these. So if you wired up on the table, and then you're going to have to show an instructor, I believe is the way it's written, don't just throw them back in the cabinet for this class. Be a friend to your classmates. Grab another coffee bucket and throw the components in it. And then the next guy just has to grab the bucket and put it together, right? That'd be nice of you. So that's what that one is. And finally, lab 9, power plant wiring inspection. You're going to take the cowling off to 414. Hopefully by the time we get towards the end, we can talk Ryan and the team into putting the 414 inside. Doesn't have to be if it's a nice day, but cowling will come off and you'll look through. It gives you a slot on your Moodle, and it doesn't really say how many how many unairworthiness problems you're trying to find on there. But I gotta look at my notes. I want to say it was 12 or 14 was kind of my number. Or if you don't make it to 12 or 14, you ain't getting 100% on the homework. If you give me 4, I'm gonna just give it back and say go keep looking. Because unless somebody cleaned them up when I wasn't looking, there's a lot of unairworthy things on the 414 wiring in the engine compartment. So it's mostly getting you to go in there and saying, well, that's not airworthy, and that's not airworthy, and you're making the list. If you get past 14, you say, good job, nice work. But if you don't make it to 14, you ain't getting 100 on this lap. There's a lot of stuff wrong in that one. I was gonna use that one for having you replace all the wires for this class, but part of the problem is a lot of those wires go from the engine all the way back through the wing, and I didn't want to do that one. So I leave them. We leave it studentized. We're not going to schematize that one. We're gonna nail that in. All of these, even with 6 hours and 6 to 8 hours, give you 26.25 hours if you do it at that speed on a class that has essentially 30 hours of lab time. So you got, if you work through it at a normal pace, you have extra time on your hands to study prepware, troubleshoot a few electrical projects. I put them all above there. Some of y'all got done with Corvettes and Custer with case. If you haven't, it'd be great timing to get your voltmeter out and troubleshoot them. And the other extra sheet that I have, I already hung one on the back wall. Read your power plant textbook. Let's see if I can get this to work this time. Come on. This is the worst camera ever. I'm gonna have to talk to somebody. I even like put this brown color down because at one point in history. Hey, good tip. All right, wire up a turbine starter mock-up. We're gonna cover undercurrent relays. I got some diagrams here. Where did wrong box? I've got this cool little kit. It is cool. You wire it up on the table, and if I get time during break today, I might do it to show you guys what's going on, or during lab today. And it's got a start button, and the motor will be like zzzz, and then once it gets up to speed, the starter kicks out. So that is not one of your labs, but it's a really cool project to wire up. So do that and kind of get to know what's going on. You could just take one of our other aircraft and do some aircraft wiring cleanup. The alternator board, the over voltage relay kind of hiccups sometimes. Partially it's because when people are finding faults, they will tend to go to that board like the landing light one, and they'll put jumpers on it. But I don't like you doing that on that board. Please try to refrain from doing that on that board, because voltage will backfeed through places it shouldn't go, and it spikes. It's a problem. So somebody could find one. Dean's like, we got them all over the place, and I'm like, oh, to work with Dean maybe, but you could replace it over voltage. Electrical math, right? We're not going to deal with impedance much this class, but you go back to, is that general math with capacitors, and inductors. It'd be a decent thing to review if you get a chance. Do an additional alternator starter. Some of our alternators are simple, some of them are a little more complicated, so you could pick a little more complicated alternator and just take it apart so you see how it works. We don't necessarily make you disconnect a Bendix starter gear engaged device. We're going to deal with those more in starting class, but you could find a manual and get to work with that a little bit. And this one is that's one of the ones I want to do, but somebody wants to help me out. Make a transistor water valve display for future generations of students. Remember all the way back in general how you had the big pipe and the transistor acts like a little valve coming in that opens a big valve. And if you don't know what I'm talking about, it'd be a good review for you to refresh yourself. I'd like kind of like Randall made the metal one, but even if it's just cardboard or metal, if we made a little flat diagram showing how a transistor acts like a water valve, that'd be kind of fun, and it'd be a great transistor review for you. So that's why, none of that stuff is busy work, it's all, tailored to help you later in life. There it is, PowerPoint 161.7 has the mag wire, I knew I put that in there somewhere. Alright, I think I covered all this stuff, I'm just gonna make sure I do it before I walk you out for a break. You'll notice, you did get a syllabus, right? I just couldn't read it. Okay. You'll notice on the syllabus, we do wiring and stuff, but we're focusing mostly on our labs, on starters, generators, alternators, because the rest is stuff I know I already covered with you in general and airframe. So I already said that, but lacing comes up. I'm not gonna do anything with lacing in power plant, as far as labs you have to do. So it'd be a decent idea to review lacing. And we're gonna talk about it, I believe today, when you're running your wires, you'll probably lace them. So, there's stuff like that that you're gonna want to say, oh, you know what, I don't remember how to do that very well, I'll go back and do it a little bit. Alright, we're gonna go take a break. On the way to the break, I'm gonna show you the alternator mock-up board. So instead of coming back at 8 o'clock, we're gonna come back at 10 after 8. It's gonna take me a minute or two to get you out there. Yeah, let's do it. So let's go out to the alternator mock-up, and then you won't have to come back in here until 10 after 8. I'm kinda like the lady Donna. She's gonna be induced into the Hall of Fame. Not that I'm gonna be induced. She got yelling. When people would start falling asleep, she'd start yelling at us. Why are you guys sleeping on me?
Hey, tell Shelby, next to the burritos.
Yeah, man.
Inspirational?
No.
Challenging?
No, yes.
Eye-opening?
So challenging that I took a nap.
Oh, you should watch it again now.
Yeah. One of the instructors did it. And it wasn't Ryan Anderson. It was the friendliest one.
Dean?
No.
Dean the friendliest one?
Yeah.
Did Lab 8 ever make it back to Matthew back there and whatnot? Does anybody know?
Not that I heard it.
Alright, let me go see if I can make a couple more copies of Lab 8. Thank you, Cheddar.
Have you, got worse than Brad at all? How he's planning to do the annual?
I haven't talked to him in 2 weeks. Last I heard was once April hits.
Does he do on the weekends or?
Usually it's Friday or Saturday, Friday, Saturday. Yeah, when it was colder, we're tending to bump it like one month. So last year we did it in the smat hanger. I think it's probably warm enough now that we'll just do it in this hanger, but I'm not sure on that.
Yeah, he and I were working on.
Cool, yeah,
The nose gear, oh man.
yeah.
It was so cool.
It's nice to have it in the cement hanger because we have tools and stuff, but the problem is, especially if it's multiple weeks, you're gonna wait.
Yeah.
So I suspect we'll just do it in his hanger.
I'm gonna text him and ask.
Yeah,
what the
sounds
plan
good.
is.
I got a list of
Stuff.
cleanup for next week.
That secondary box might be a signal relay, because it gets relayed from the stator.
team effort.
I've never done it.
No, you did it.
Yeah.
Yeah.
Let's see, so that's going clockwise. Trying to remember if it still goes clockwise. Switch it. Okay, good. Before I explain it wrong. Whoa. Too much fun. What's this? All right, welcome back. Matthew, did you end up with lab, was it 8 or 7? Did you end up with 7 or 8? I have 2 8s and 2 7s here, so between your last row, sort out what you guys know. Hot off the press. The other thing that's hot off the press, takes a long time to print double-sided, is these. You will use these before your next break, hopefully. If I did it right, double check, because actually I didn't check. One side should be continuous, the other side should be intermittent. Did I do it right? Oh, okay. I have the plastic coated versions if you want to just practice in class or whatnot. We leave these at SMAT forever. I'll leave these up here in case you run out of that, you don't want to make new copies, or you could make copies of those. And I made an executive decision. The box and the shielded mag wire will live right here for this class. So that's where your new mag wire and your old mag wire will live. So there's that. Okay. I got to show off Sam. Sorry. I was stuck on the G for his last name. I'm like, yeah, Gan. Sorry, I'm getting old. I was stuck on the guy. So we had a student Guy a year or 2 ago, and it popped into my head, and I'm like, get out. Get out. Sam and Randall's handiwork here. We got some, you guys saw my fishing mag. I can't even get it off. So we labeled them, if you look close when you're looking at this, there's a S for the south side and an N for the north side. So you can use your right hand rules. I don't even think those show up in my lecture today. Not a bad idea to review. We do have these that will also live up here. We're going to deal with the alternator one a little bit more when we get into alternator control. But a little review of right hand rule, left hand rule. If you wire it up to a battery and turn the switch on, woo! And you notice that was, sometimes it doesn't want to start if you don't start it in exactly the right spot. That was spinning counterclockwise, so you could like go through and be like, okay, right hand, it's going to go that way. If you reverse the polarity, because we reversed some of the hand rule stuff, especially if you start in the right spot, now it goes the other way. So it's kind of fun. I'd recommend when you get a chance during lab or whenever, come take a look at it. You can actually, and we might do it when we do alternators, you can hook a voltmeter up to here and hook a drill up to here and spin it and create a voltage as well. So it's actually a generator at that point, right? And you can figure out, hey, what's positive? Is it going to be positive voltage or negative from here to here? So good job, Sam and Randall. That was the official intro for this. Now, if you leave this on, the wires will get hot. We didn't exactly figure out the cooling. Well, it's crude. Yeah. So don't, if it like sticks and you're like, and you're playing with it for a while, just they'll get hot. We're gonna cover hot wires today, but just be careful with your hot wires. All right. Today's actual lecture is gonna go over this stuff. Fun stuff. Pages 47, 53. Read them when you get a chance. Be a good idea. Also, charts, diagrams. I did not grab my book out of my office. I'm gonna have to run into my office when I get to a certain slide and grab my So I'm gonna have to read stuff. If you have your books in front of you or opened up on your computer, that will help you follow along as well. This seems like an out of place slide because it slightly is. I call these handshake connections. Last year when they took apart is that the 210? Looks like the 210. Apparently none of the students knew what this connection was, and I was like, well, we're not done yet, but maybe I think I covered these in airframe with you guys this year though, right? Where they kind of like, so I call them handshake, I like it. Technically the aviation world will call them like a knife connection, it's kind of a weird name. After you make them, they expect you to shrink wrap it so that it's protected. We're gonna cover it, I believe today, when we're talking splices. That's an interesting concept. Is that a splice? We're in a gray area between, is that an actual connection that we made, or is it a splice? Oh, that's tricky. That's a tricky question. Same concept would apply to a Molex connection. So a lot of Cessna aircraft came out of the factory, and they had a wire that ran through the tail out to the tail beacon light, and you couldn't take that cone off the tail without either disassembling the light or cutting the wire. It was like, well, how do you do a 100-hour then? So most mechanics will add a Molex connection at that tail, and then now we're back to, is that a splice? That wasn't on the fact, and I don't have an answer to that. I would call it, you added a connector, a connection, and if you were doing that, that'd be a great thing to write in a logbook, right? You worked on aircraft, added Molex connection to tail cone in accordance with AC 43 or something like that. It is just an electrical connection. We're gonna cover some of the stuff that are specific to specific aircraft in a minute. Mr. Ward.
Did they replace those last year? Was this one not on?
Maybe they put a Molex in because those are a hassle, but should have been out by the tail cone. I think it was 210 because of that stripe, but or maybe you didn't see it because it's shrink wrapped and you didn't know it was there. That's another possibility, right? So handshake connection, you don't see them as much anymore, but absolutely they gotta have shrink wrap on them. All right. Fun with electricity. We're gonna go back, we're gonna do a little math. I got your names all set. I believe I put Cheddar back down to one man. So, help me out. We're gonna draw a big triangle. And if I'm doing mathematics, what goes in the top one, Carter? Ohm's law. Voltage, yes. Volts. Volts equals Jedediah. Give me something for another box.
Ohms. Resistance.
Just one. You're gonna go with which one? Ohms. Okay. If somebody wants to take your resistance, we'll let them add it to one or the other. Because part of this is just a reminder, when I was down at Baker School of Aeronautics, even though she was like, for 8 hours a day, 3 days in a row, I took 5 practice tests before I took the real one on Thursday. Because even though it's a lot of info, there's something about repeating it that helps us remember, right? So that's what we're doing. Ava, give me another something to put in a box. I got at least 8 words, letters, or things left, so you still have an easier one. Where is Ava? Ava?
Current,
What?
current.
She's filling in for Ava. Current. Where's current gonna go?
Ava is currently not here.
Thank you, Joe.
Next to us.
All right, current. So if I, as a review, multiply my ohms by my current, I will get what my voltage is. So it's gonna get a little bit trickier. We're gonna see if we can fill it in. I think we can go up to like 6 or 7 more words or stuff in there. So Corbin, give me another something for a box. Might be the same thing, just another either way of saying it or the letter we use. What? I, and where's that going? Current is signified by I in formulas. Nice job, Corbin. Thomas,
You could use E instead of volts.
I can use E instead of volts. Anybody remember why it's an E? I hear mumbling. I wasn't sure until after I said it, so I was really scared. I hope you'd get it. Any hands up? Corbin!
I just want to guess because E was already something else.
Not quite.
Electromotive.
Electromotive force. Yes, electromotive force. I prefer it to be electromotive pressure because volts is a pressure, but yeah. EMF ended up being E for electromotive force. It's way back from, back in ohms, back before, we had all that. Amanda Dennison, give me another something. Another letter or word or symbol.
This.
Do that one more time. Okay, where does it go? Above the ohms. Okay, she did this with her finger.
You could also do a V. No, not.
One at a time, Amanda.
You already did.
We're not letting you take all that. All right, Shane. This will be R for ohms. Why is it an R? Okay. Now, I don't always, yeah, exactly. I'm going to draw a line down and say resist. Uh-oh. Resistance. All right. Now, we could get a little tricky here. I'm going to stop drawing names because, oh no, we got at least one more. All right, we need, yeah. There's one. James Goodhue. It's been a couple weeks, sorry guys. I'm like, I know it's over here somewhere.
What's the question?
I need another word, letter, something that we use, I'll give you a clue, something that we use in Ohm's law all the time. All the time. How many? Amps. Thank you. Where would that go? With current, yep. Amps, which depending on who's writing it, maybe it's an A in the formula. So all these letters get exchanged and such like that. So volts, E, amps, current, R, yeah. Okay, I'm thinking on my feet. I think we're missing 2 or 3 more. One of them would be in here, and it would kind of replace our resistance. So I'm thinking of one, but anybody else, what else could we put in there that might show up on questions, especially verbal ones? Impedance, that's right. Impedance. So if we're not dealing with a straight resistance, formula still works for current, right? So if we switched it to an impedance down here, well now we've got another something we could put in. Anybody? What do we use for impedance?
Is that Z?
Yes, that's right, is Z goes in there for impedance. So I feel like there should be 1 or 2 more up there in volts, but I can't think of them off the top of my head. So that was a good review. Okay. All right. So with that said, we're going to draw ourselves a basic little diagram. We'll do a plus. We'll do a minus. We're going to go through. Why not put it through a switch? Everybody likes switches. Oh, it's getting tricky. Oh, we're advanced now. We're advanced now. Okay, let's say I've got a 12 volt battery, and I've got a resistor that is 6 ohms. What would be my amperage? Caleb.
12 volts, 6 ohms.
I gave you that info, yes?
Yes.
Drawing with blank letters.
Tiki, help them out.
2.
2. That's right. So 12 divided by 6 would be 2. 2 times 6 is 12. All right. Now, if I were to switch this without switching anything else in the system to 24 volts, Christian, now what is my amperage? I switched my voltage to 24. So I got 24 volts, 6 ohms. Oh, you Christian. He's cheddar and he's riding. Yes, 24 divided by 6 is 4. That is correct. We doubled our amperage. Good job. All right, now I come in here and I turn another light bulb or something on. Maybe that was my landing light, and this is a taxiway light or something like that. Sam, what is the total resistance of my circuit? See, this is why we review. Everybody's like, I thought we were done with that stuff. Here comes the Calvary. This is why you should all be doing the math if it's not your name. David White.
8 amps.
Is that the question I asked? No. Total resistance.
Sorry.
He's like 3 steps ahead of me.
3 ohms.
3 ohms. So these are in parallel, right? And resistors in parallel, you either have to do that really long formula, 1 over RT equals 1 over R1. Or if they're the exact same resistance, it makes it really easy. You just divide it by how many there are. So 6 divided by 2, 3 ohms. So very good. How many amps then? 8. So 24 volts divided by total resistance we said was 3. Yeah, that works. Good job. He's thinking multiple questions ahead of us. Multiple questions ahead of us. All right, we're gonna get. Let's see here. We'll go one trickier one and say, now we add 3 ohm in there. All right, now what's my total resistance? Randall. 6. Okay, good. I can't fool that guy. So if this section was 3 ohms, but it's in series with another 3, that's 6 ohms total resistance. That's right. Okay. I'll be back in a minute. The question is going to be, the first person that can tell me the amperage in the system, I'm changing some numbers. First person that can tell me the amperage in the system will get a pat on the back. Randall's got it. Christian's got it. Maybe I should raise your hand when you know.
I think so.
Oh, it hurts. It hurts. Chatter. Just look at the picture. This is like, what was that game we played at Christmas? Be like, the book game.
Once you know, you know.
Once you know, you know. Oh. That was dirty. That's 0. We have 0 ohms. Oh, sorry, 0 amps, infinite ohms. We have an open circuit here. So yeah, if there's no path for electricity, we won't have any amperage. That's infinite resistance, which is 0 ohms. Yeah.
So do you tap all of us on the phone?
I will. You know what? When we go, I'll stand by the door. As Dean would say, we'll make it, how does he say? Hard enough, low enough, long enough.
What? Down the back.
Yeah. That's an old saying for when you guys are messing up. Give them a pat on the back. Just make sure it's hard enough, low enough, and long enough to solve the problem. All right. I'm not going to go into impedance. You know, we could draw. This will be fun, just for the fun of it. We could draw a system that had a capacitor and an inductor. We'll do a switch in there for the fun of it. coming back to the battery. Oh, resistor too, right? I'll make the switch closed for you, Cheddar. There we go. All right, and we could say that that one was 3 farads, and this one was 3 henries, and that's 12 volts. And we could ask the question to say, how much current do we have in this system? Randall? I don't care. Why don't I care? I've got a DC power source, people. What's going to happen with that capacitor as soon as it gets charged up? No flow, right? So a little bit of review. If we got systems like this, and you're doing crazy impedance math, we're doing it with AC power. Because if I throw a capacitor in series with anything DC, it'll get itself charged up to 12 volts, opposite, and then no more current flow. So you could say, well, for a fraction of a second, you might have, but yeah, it's not. So if I was gonna do that drawing, I would have to do this, right? There. Now we could do some math, but I don't really want to do it today. So I'm not gonna go back to that. Not a bad idea if you wanna go back on your own. And you need a resistance, but I'm not gonna go that deep. It takes time. It takes time, and I don't wanna spend all that time in here. But you can get in your book and you can do that. All right. Gotta draw my little thing back up. Switch. Let's make it a light bulb this time. We'll connect it all the way up. So, in our DC circuit, I always teach conventional because I'm old school. So, which direction is the current flowing in my system, Jedediah? Let's see, counterclockwise. So this way?
Yes.
That's incorrect for conventional. So conventional always goes from positive to negative. Electron flow goes counterclockwise. You might work for the FAA. The FAA likes to draw it with electron flow. I teach conventional flow because if you Google anything historically, all that stuff, conventional is what we draw. Every once in a while, so yeah, the FAA draws all their pictures reversed of what I have on my PowerPoints. So just a little review for that. If you're doing electron flow, they'll say the electrons flow a certain direction. If I was going to add a, whatever we call those, what do we call those? Diodes, that's right. Would that work? No, because diodes are drawn for conventional flow with the arrow in the diode pointing the direction it will allow current to go. So if I had a diode in a battery, I would have to have the diode in that orientation to actually have flow through the diode. So diodes, as a reminder, they're like a check valve for electricity. They only allow current flow in one direction. I wrote up here, I actually had to review this on the plane. I was like, what were those 4 letters again? It was CCC something. So it's just alphabetical order. It's like when you can't remember. If I'm up here stuttering like an old fool because I'm getting there. I'm like, wow, CCD. I finally make it to it's alphabetical order. CCCD. Yeah, so CCCD, conventional current cathode departs. So when we say departs, it's like leaves the device. If you're going to use this mnemonic cheat, they spell it weird, right? Mnemonic cheat. So if you said this device, which side is the current leaving the device? You would say it's leaving from the cathode side. The K being the cathode, even though cathode is spelled with a C. But you get the idea. So conventional current cathode departs. So if you were to get a question on your written that said when a battery is in use, is the positive terminal or the negative terminal the cathode? Oh boy, wait, CD. All right, so if I said this device in conventional current, which one is it departing? I'm departing the positive terminal. So when you're using a battery, the positive terminal is the cathode with conventional current. So conventional current, cathode departs. If they ask you an electron flow, which terminal does the current depart when you're discharging a battery? You go, oh, electron flow, I'd have to change it up because the old stuttering man is conventional. He doesn't use the new electron. So then it'd be the negative. But if we were to take this battery and we're going to put, I was going to say an alternator, but I don't want to confuse anybody, an alternator with a rectifier bridge. So we're going to output DC, and I'm going to just hook him right up to my battery. I'm going to recharge my battery. While I'm recharging my battery, which terminal is the cathode? The other side, good answer, the other side. So we're actually going to suck charge out of the negative, if you will, and jam it, because our alternator's doing work. We're going to jam that charge back into the positive. So if we're charging the battery, the negative is actually the cathode, if you want to answer the question. So try to get that in your head. Conventional current cathode departs, CD. That'll help you know anode, cathode, and it helps you memorize what's going on with our batteries. That is a prepware question that shows up some places. All right.
Hey, Case.
Yes.
Was that review time? Were you the pilot, or was this commercial? When you were reviewing this.
Yeah, commercial flight. I was not flying.
Just
Yes.
curious.
All right.
Keep it realistic.
Remember, voltage is pressure difference, so it's always pressure difference between two things. So we're going to draw a little timeline up a minute on our board. So if we put a timeline up here, time going that way. So this is some time ago. This is timeline. All right. Now pressure difference. We're gonna read basically to ground for the moment. So we're gonna say, what's the pressure difference to ground? Now, if I was gonna, let's do this. Gotta keep you guys awake. Should I just pick somebody that looks like they're sleeping? Be like, hi. No, I'll Ava, where is Ava? I'm gonna have to mark her absent if I get that one more time. Give myself a little note and be like, are you okay, Ava? Alright, try again. Corbin. Oh, you were answering bonus questions? Come on up, Corbin. Draw me my voltage line across my timeline for a, let's make this fun. We'll say 24 volt, for my 24 volt battery. So I turn the power on to a light bulb, 24 volt battery. What is my voltage going to look like across that timeline? If you need a picture, so if I put a voltmeter across my light bulb, over time, what's that going to look like?
I don't remember.
No? Oh, I pick a friend, phone a friend.
Shane, I like the way you look at it.
I'll give you a clue, Shane. This one is not intended to be a trick question.
Would you mind repeating the question? I'm a little confused.
So this is a timeline.
Okay.
Let's say this is now, and I turn the switch on that I didn't. So I turn the switch on right now,
Okay.
and here's 10 seconds from now.
Okay.
And I want to know what's my voltmeter going to show 1 second from now, 2 seconds from now, 3 seconds from now. 4 seconds from now?
This is an alternator.
That's definitely a battery.
Sorry, so, okay, it's a 24-volt battery?
24 volt yeah, sure. Let me put that.
I mean,
This is why we're reviewing. This is why we're
if it's
reviewing.
instantaneous.
I will accept that answer.
Okay.
All right, thank you.
I was like, sinusoidal wave.
That's not an alternator.
Okay.
Marcy,
You draw the batteries the correct way.
what do you mean?
Like,
Oh, you want them like this?
yeah.
The correct way.
That's not, you'll never see that on a wiring diagram, and it's slowly driving me crazy.
Well, and technically that's not even the correct way because both ends are positive.
This one says negative.
Well, no, the one you just,
Yeah. I will try to do that. I will try. I'm trying to
well, we
I'm
do
trying to
need
simplify
practice.
things here.
We need practice reading real diagrams.
Yeah.
This is practically AVPs. We've been through general, we've been through airframe. This is power plant. Give it to us, right?
Alright. In a DC direct current, right? DC direct current. That's what our timeline would look like. We're gonna have 24 volts, it's gonna be steady. Now, I guess I could have told Shane, okay, right here in time is where I close the switch, and he would have had to been like, what? But yeah, you get the idea, right? So that's a DC timeline, and we would say that's the voltage wave, but it's not much of a wave. So if we switch it over, Marcy, to an alternator, is that okay? Okay. If we switch it, I was like, I'm trying to think if I have another symbol for an alternator. If we switch it over to an alternator, now we've got an issue, right? Because the voltage goes up and down, up and down. And I gotta start somewhere, so I'm just gonna pick a 24 volt point to start with. So I'm just gonna pick it here, and we gotta know how many hertz, or the frequency that we're cycling at. I'll just draw it like a sine wave, and we didn't necessarily set our hertz or frequency, how long it takes between these 2 points. They do like that question for large commercial aircraft. What's our normal frequency, just for review? 400 hertz is our typical, which means we would have 400 of those in a second, and my room's not long enough to cover a second anymore. But, so that's a 400th of a second that we just drew there, basically. So, hertz frequency 400. Now, if I hooked up a voltmeter to that light bulb, there's a really weird question here where if you said, what's the voltmeter gonna show if because it's not gonna switch the number on me 400 times a second, right? It's not gonna, I don't have that fancy of a voltmeter, that'd be like an oscilloscope. And even that, so we'd say, what is my voltmeter gonna show? Now, I could trick you and say, what's the average voltage? It's not a good word though, right? Because technically, 0. The average, because if I'm technically 0 volts. Well, if the average voltage was 0, because I got 24 volt positive down to 24 volt negative, and you go, well, if you got average of 0 volts, you're not gonna have any current through your light bulb case. And I go, well, okay, so I can't really use that word average voltage. So we use the RMS, the root mean square voltage, and that's what your voltmeter will show you when you hook a voltmeter in AC mode up to an alternator. So on this system, should I draw it? Yeah, you guys should know this. If you need help, you can ask a friend, Amanda. So if I hook that up to my voltmeter and said, hey, what's my voltmeter gonna show in this AC current? You would expect to see on the little digital screen.
At which moment, right now?
This is doing it 400 times a second. So I'm just saying over average of the next 20 seconds. You would be sorely disappointed. Sorely disappointed. Matthew.
Approximately 17 volts.
approximately 17 volts. You're gonna be about here, 17 volts. So RMS, root mean squared, is the square root of 2 multiplied by whatever the peak voltage is. So that little review, 24 volts in this system was a peak voltage. So if we want to know RMS voltage, and we don't really want to say average, but RMS voltage is going to be basically our peak times the square root of 2. And square root of 2 ends up being 1.41-ish. So 1.41 times 24 should equal 17. Cheddar. Okay, Matthew.
Divided by 2.
Divided by. Oh, you're right, because you'd have to multiply it by 1 over 1.41, which is 0.7, if I'm not mistaken. Sorry. If you get a higher number for your RMS voltage than your original voltage started out, you should do a sanity check and say, well, it can't be higher. It's got to be a little less, yeah. So, okay. Good review. So that was if we had our light bulb or whatever, and it's on that sine wave, and hey, where are we at? What is going on with this thing? And I notice I still referenced ground because with our whole system, we're still going to do that. But I don't want to get too far off in the weeds. So we're going to move on slightly. Most of our alternators that we'll end up dealing with have 3 different windings in them as a reminder. So we'll have winding 1, I'll put it here, here, here. Let's see if I can connect it. Winding 2, and winding 3. Now, if we are in that alternator, we can pick between one of our terminals. Remember, our alternators are either wound in a delta configuration or they're wound in a Y configuration. Either way, we have 3 terminals on our alternator. We're going to cover this in a lot more detail later on in that alternator class. But from one terminal to another, let's say this is the red, this is the green, this is the black. If I take one point in time, at that point in time, what would my voltage be if I were to put a voltmeter on between green and black? Oh, looks like James Goodhue gets that one. At that red line in time, what's the voltage difference between my green and black terminals?
You say voltage difference?
Yeah, well, so voltage, pressure difference is a voltage. What's my voltage?
At its lowest point.
Is that 0 then?
Almost negative.
I would go with 0, because green and black, if they're the same point in space, so they are not separate. But if I said, hey, I'm going to put a voltmeter between green and red, now I have a number that is, well, however far that is. And we could do some math. I guess that's 17 up there, and that one down there is probably the peak at 24. And we got to do some math. And we're never really going to do that math, but it's just getting that understanding that as we go through time in an alternator, the voltages are drastically changing between all the different phases and terminals, and we'll get back into some rectifiers and whatnot. But we're just doing the review for now of DC versus AC alternating current, and kind of reviewing, getting our head back on straight. So I think that's as far as I want to go on that slide. Simplify it back down. Let's back it back off to stuff we can do math on. Assuming we don't have a capacitive or inductive circuit, because if our circuit is more capacitive than inductive or inductive versus capacitive, it messes with things. But if we're saying, hey, it's a pure resistance circuit, and I hook my circuit up to a resistor, it's 12 volts. I got 2 ohms. How many amps do I have? Oh, I feel like I went backwards here. Kurt? 6 amps, that's right. Very good. Now, let's cut a wire. We'll hook up an alternator. We'll hook it up to the same circuit. How many volts RMS would I have to have the same 6 amps? Isaiah? Heiss? How many volts RMS? I'm trying to be tricky.
Can you explain that question a little more time?
Well, if I've got an alternator, I could either have peak voltage or RMS voltage. I could ask you kind of either way, but I just threw an extra word in there to make you stumble over your feet. So how many volts RMS would I have to have? Oh, do you want 12? So RMS volts to give me the same 6 amps. It's 12. So, as long as you're talking RMS, which is, we don't like to use the word average, but effective, maybe effective would be a good word to use for RMS, right? So, as long as the RMS voltage, which is the effective voltage of our alternator, is the same 12 volts RMS, you get to use the triangle still. We still get to use volts equals resistance over current. So, I tripped him up by saying RMS voltage. What's my RMS voltage? In a system that I have a 12 RMS voltage running this, if you were to take an instantaneous voltage, so I got this timeline, I got my voltage doing that, and I said, I need an instantaneous voltage. Now the problem with that is you have to have an instant, right? I'd have to give you an instant. If I picked that instant, I'd get 0 volts. If I picked that instant, I'm going to get the maximum voltage, and I'm almost there. So if it's the maximum voltage on a 12 volt RMS system, what would be my maximum instantaneous voltage on that? We're getting through the cup. Matthew. Approximately 17. So you're going to take your 12, this time you are going to multiply it by 1.41. 12 times 1.41 is our maximum, we might actually call it peak, right? So our peak instantaneous voltage would be 17. But as long as we're just dealing with resistance, 12 volts DC will behave the same as 12 volts AC. And I just threw RMS in there just to make sure that we're all like, okay, so RMS is my effective 12 volts, AC is the same as 12 volts DC through a resistive load, and we're going to run with that. All right, I'm going to check with Marcy.
Why'd you cut the wire?
I cut the wire because I didn't want any voltage going through that side of the system.
Okay.
Yeah. All I got to do is cut one leg and I don't have voltage anymore, right? So I turned off the battery. Yep.
That was my question.
Okay, you all want to know why I cut? Because if I didn't cut the wire and we got an alternator going, what? My battery's not gonna. That's something. I don't know what's gonna happen, but something weird's gonna happen. It's not gonna be good. We're probably gonna have flames and sparks and
We should try.
stuff like that. Yeah, I don't think it'd be. good. All right. All right. Whoa. There. Ooh. All right, we're going to shift gears. Actually, did I miss a slide? No, I didn't. We are going to shift gears away from just electrical theory review, Ohm's law, AC, DC, and we're going to shift back into what you might consider airframe, but we're in power plant, just wire routing, labeling. It's still review, minutes till your next break is what I'm hoping for. We'll see how we get there. All right, through all these lectures, I'm just gonna go with copper wire. It's copper wire in your aircraft. There are a couple prepware questions that talk about aluminum wire. Very rare, you'll hardly ever see aluminum wire in aircraft anymore. They like you to know some things about aluminum wire just because, well, it's in some of them. So these are just straight up memorizing things, which you need to know. Copper wire has a higher conductivity. You can get that chart out of your book. It compares copper wire to aluminum wire. Conductivity basically just means how well it conducts electricity. Another way to phrase that would be, what's the ohms per 1,000 foot of this wire? Well, the ohms is going to be less per 1,000 foot of the exact same size wire in a copper wire versus an aluminum wire. So copper wire has a higher conductivity. It conducts electricity better. We would like that, right? That's a good thing. It's more ductile. Ductile? Ductile means you can bend it and stuff without it breaking, without having problems. So it's easier to work with copper wire. So those two things alone would be like, I'm always going to use it. And I'm almost there, Amanda. The last one's tensile strength. Is if I get a crack or I'm pulling on it, it's just stronger. It's stronger stuff. It's easier to solder, but it is slightly more expensive. I don't know if you guys knew this, but you know aluminum is the most common metallic element in the world, in the Earth's crust. I learned that the other day. I thought it would be iron or something, but aluminum is actually the most common. It's just fairly expensive to extract, the process of getting it out. So, fun stuff for today. There's more aluminum in the crust of the Earth than any other metal. That's kind of cool. But, and aluminum's very light. So basically the only reason we're going to use aluminum is it's cheaper because it's all over the place, even though it does take a little bit of work to get out. It is cheaper, it's very light. So for a little bit, when copper got super expensive, especially in the 70s, I think, in the 70s, they said, let's run some aluminum wires. And they shortly found out it was a bad idea because aluminum corrodes faster. And if you nick an aluminum wire, it's not as strong. So they do have some questions about aluminum versus copper. I think we covered a chart that if you're converting, you can go to that chart. I just say don't do it. If you have this kind of memorized, you're good to go. Okay, Amanda. Okay, I covered it. Very good. So from now on, we're just gonna go with, you're dealing with copper wire. If you're not dealing with copper wire, stop, turn your head around backwards and say, okay, I gotta go slow because all of the general rules of thumb might not necessarily apply. So a couple terminologies, wire, conductor, stranded insulation. So usually when we use the word wire, we are talking a conductor inside an insulated sheath. That's usually what we refer to as a wire. A conductor is something that electricity passes through. So if we had a stranded wire, so I've got something inside a sheath that electricity can go through, we're going to call that a stranded wire because the whole thing is the wire. We usually are just going to call one of those a conductor, but you know, we change words around a little bit, so maybe we say the conductor is the whole section. But an individual strand would be just one piece, right? So stranded conductor. A solid conductor, on the other hand, if we throw solid in front of it, well, now we know it's not stranded. So that's how we use the stranded solid. If we have a cable, in aviation, we typically are saying we have multiple wires, so multiple insulated conductors run through the same, usually it's one outer sheath. So maybe I have four separated insulated wires all run together with another insulator on the outside. We'll typically call that a cable. Not to be confused with your flight class cables that are just steel, right? So an electrical cable is multiple wires all run together. Twisted pair, it's not really a cable because the outside of the twisted pair is not insulated around the outside. So that's why on a twisted pair, instead of saying a two-wire cable, we usually just say, it's a twisted pair. Plus, it tells us it's twisted.
So for an Ethernet, when it's many twisted pairs surrounded by an insulated sheath, is that a cable or is that, no?
I would would say they're giving you extra info on your cable. Yeah, I would call your twisted pair a cable if it's insulated. But, yeah, that's where we get where it's like, let's just figure out where we're at. We also have coaxial cable as a reminder. So if we have one conductor on the inside and one conductor that might look like a shield, but back from communications class, we actually have current going through that outside layer. As long as the center point of both of those circles is the same point in space, we call that coaxial cable. They share the same axis. So coaxial cable is two conductors inside an insulated sheet, right? So coaxial cable. We do coaxial because if I got amperage one way through the inside and amperage the other way through the outside, but they share the same axis, the same center, any radio frequencies is negated because they're putting off competing EMF signals that just cancel each other. That's why we use our coaxial cable. Twisted pairs, they will do because they're like, well, I mean, we don't really need to run it through a coaxial cable, but we do want to knock down the radio frequency a little bit. So let's split the difference. Let's go halfway. And they'll run typically an AC power source. Maybe you're powering LCD display with AC power. If they do that, because you've got AC power, you'd have amperage going back and forth, back and forth, back and forth. Instead of running it through a coax cable, they'll run it through a twisted pair, and basically that twisted pair will do a pretty good job of knocking down any EMF interference that's heading to that LCD display or whatever they're powering with it. Part of why you can get away with that on a twisted pair is coax cable frequencies are very high. What's our normal comm frequency? Let's say, yeah, just communications. It's like 122.8 what? Megahertz. I think, yeah. Which is mega is like 1,000, right? Really fast. Well, if we're powering an LCD display, what's our frequency most likely? In aircraft. What?
Really, really high?
Nope. Aircraft frequency typically.
Oh, 400.
400. So at 400 hertz, well, we'll just run it through a twisted pair, and that'll do a pretty good job of knocking down any radio interference that we have. All right. As a review, we have this fancy AWG wire gauge checker. They are made for solid wire. They are not made to put stranded wire in. You might find a manufacturer that makes one that's adjusted for stranded, but they're lying to you, they're cheating, because depending on how tight the strands are, it can change what size the wire is. So yeah, you might find one that electricians use, but you shouldn't. So these are made for solid wires. So you take one solid wire, how thick is it between the outside? So that's a 0 AWG wire pictured there. If you want to know that you have a stranded wire with, let's say, 16 strands, and you want to know what the AWG is, number one, what's the easiest way to know? It should be printed on the wire. So let's not get too complicated. Read the wire. How many AWG is this? Number two, if we're in an aircraft, what's the other way to know?
Look at the manual.
Look at the manual, the wiring diagram, and we'll cover that later. It will say what gauge wire that is. So if you're replacing a wire in an aircraft, and you're like, oh, what gauge do I use? Better than measuring is go to the wiring diagram and say, what gauge wire should this be, right? So it should be printed on it, should be in the wiring diagram. Last case scenario, you could go to like using one of these or measuring one wire and going to our circular mill thing. So a quick review on circular mill. Let's say we had 16 individual wires at 24 gauge. My IA test, they said they were AN 24s. And I'm like, what? I don't know where they're getting info from. It's AWG. AWG. So even the FAA, they can't get their stories right. So what I do is I go to 24 AWG. I go over to, the best way is circular mills. It's hard to read that, but it's 404 circular mils. As a reminder, a circular mil is, I'm gonna blow this up and say that is 1/1000th of an inch. So if I had a circular thing that was 1/1000th of an inch, that's 1 circular mil. If I had a box and I wanted to know how many circular mils that cross-section of the box was, it gets a little bit tricky to draw a bunch of circles in to figure it out, because you have those gaps, right? But that's where that circular mils comes from. They're basically asking, instead of how many square mils that box is, they're saying, well, how many circular mils would it be? So the numbers are slightly off. So we're 404 circular 1/1000th of an inch things thick in a 24 gauge wire. That is basically a direct relationship to the resistance of our wire. So if we come over here, I'm just gonna pick the 25 degree, and I'm gonna say that's 26.2, I believe, ohms per 1,000 foot of a 24 gauge wire. So I said I have 16 of those, right? So if I want to know what my resistance is per 1,000 foot, if I have 16 of them, well, I could draw you a wiring diagram and draw 16 of those individual wires, and I'm going to stop drawing, all in parallel. That's what they're doing, right? We would say I would take my resistance and divide it by 16. But I have 16 individual strands that are 24 gauge. We go, oh, I don't know, what was my AWG to start with? So I have to take that circular mils, multiply it by 16. Can somebody do 404 times 16? 6,400. And I don't have the exact number. This one's 6530. So we're going to be sitting pretty close to that one right there. So if I have 16 wires at 24 AWG, I have a 12 AWG wire. And just for the fun of it, we'll run over to my 12 AWG and say, oh, look at that, 1.62 ohms per 1,000 foot. If you take your calculator and divide 26.2 by 16, it should come out pretty close to 1.62 ohms, right? So just a little refresher on circular mills and how to know wire sizes. But the reality is we're gonna look at the wiring diagram first. We're gonna look at what's printed on the wire second. And most of measuring this is just so you understand what's going on.
I may have missed something. You went 24 over to circular mills.
So I'm gonna say I had one wire bundle that had 16 individual conductors that were 24 gauge.
I guess my question is, why did you go over to the ohms? Do you need?
So if I wanted to know how much ohms of resistance that wire was,
the strand?
one strand of 24 is 26 ohms per 1,000 foot. Our big one that had 16 of those individual strands that are 24 gauge, turns out it was a 12 AWG for the whole thing. Our 12 was 1.62, so it's just a review to show you that the resistance of the whole stranded, I'm going to hesitate to use the word bundle, but bundle is going to be the same resistance of if you were to take every one of those wires and say, what are they each? Multiply them up.
I'm sorry, how did you again determine that the 16 at 24 was at 12?
Yeah, we'll do it one more time. We'll give different numbers. Let's say I've got a stranded wire and I have, I'm going to go with 32 conductors in it. And each one is a 28 AWG. So if I got 32 conductors that are each 28 AWG, what is my actual wire size of the whole thing? So we're going to start out with 28 AWG, which is down here. And we're going to say, okay, at 28, I'm going to go to circular mills. What we've seen is I could actually go all the way to ohms, but I don't want to. I'm going to say 160. I say, okay, 160 Now, how many circular mills total would I have when I add them all up? 160 times 32 is gonna be 5,120. So I'm just gonna go up my chart until I get to 5,120. Here's 5,180. So that would be a 13 gauge if it was that configuration. Yep, well, I'm glad you asked, because you can use this chart a couple different ways. We're after the concept. Okay. Factors for wire size. How big of a wire do I need to run in my aircraft? The biggie is what we're going to call power loss. Voltage drop might be another way of putting it, is we don't want to waste energy, but we're going to have a little bit. We have amperage through a resistance, right? All of our wires do have a certain resistance per 1,000 foot. So if I'm moving amperage through a resistance, Ohm law says I'm going to drop some voltage in the process, right? So if I'm dropping voltage in the process, we're going to say, okay, well, how much voltage am I allowed to drop in an aircraft wire? So we can get really complicated. This is review, but we can get really complicated and use like 16, well, okay, not 16, I exaggerate, four different charts based on continuous, intermittent, altitude, temperature of the wire. Most of it has to do with we don't want to cook our wires. And the wire itself, the copper can get really hot and not be damaged, right? So we're actually not worried about the copper. What are we worried about? Insulation. So most of it is actually how much heat can the insulation take. If you buy more expensive wire, it can take higher heat. So they give us this chart and say, well, if you let your wire get up to 200 degrees Celsius, that's hot. I'm a Fahrenheit guy. That's like a lot. It's a lot. It's 200 times 1.8 minus 32. That's how much it is. It's a lot. 400 somewhere. Most of our wiring, we're not going to let it get that hot. But they give us options. If we wanted to say, hey, I'll let your wire get super hot. If I had a 16 gauge wire, instead of saying, hey, we got to limit that wire to 7 amps, they might say, well, as long as you're okay with your wire getting hot, I'll let you do 14 amps through that wire. So there are these little bit more complicated charts based on how hot can I let my wire get. And you'd have to use this now in altitude, now is it in bundle, because we're trying to really fine tune it. These are going to be used more by an aircraft manufacturer, not so much by you guys. They just want you to know how they get to those numbers eventually. Part of the reason we can do so much more amperage, the hotter the wire gets, the faster it's going to reject heat is part of it, right? So hotter it gets, the resistance goes up, which means the voltage drop goes up, but also it's going to reject heat faster. So pretty complicated charts, and that's why it's not just one easy chart. We don't really want to use that chart, but that's the underlying reason for why we can switch our wire size around based on lots more charts. But we're going to use the simple ones.
Is that one on a written?
I don't think that shows up on the written. They might ask a question on, if it is, they'll give you the figure. I'll put it that way, and it'll be in a book. But I am not aware of it. It usually has more to do with they want you to understand why the manufacturer can get away with running potentially smaller wires than show up on the chart you're going to use. So, when I do the math, the general rule of thumb, and you don't have to remember this number, but just the general rule of thumb for your FYI, is usually you can get away with about 20% more current if you want to go through all the engineering steps than you can get away with using the wiring chart that you guys have. So general rule of thumb, 20%. If you really start going crazy, yeah, it can get up to 50%. You can double it like we saw. But generally it's like 20%. And they say, our A&P mechanics, let's just make sure the wire's 20% bigger and not worry about burning the airplane down. So that's why they give us a more simplified chart. Now, on the writtens, you might get words in a question. There are always words in a question. instead of charts. And they'll say, what's the allowable voltage drop in aviation? And the allowable voltage drop is, there's a generality of saying 5%, but you won't ever hear that. You'll get this chart instead. They'll say, well, on a 14-volt system, if it's continuous operation, we'll let you drop half a volt. If it's intermittent operation, we'll let you drop 1 volt. On a 28 volt, or you can say 24, but they give you the chart. This chart here, that is the chart for when they say what's allowable voltage drop. You're probably never going to see a 5%. They will ask you these numbers, giving you the chart. But this is 5%, right? So one of those is 5%. It's much higher than 2%. There's a question that will trip you up, especially in power plant. If they ask, what's the allowable voltage drop between a power source and a bus? What's the allowable voltage drop between a power source and a bus? So either between the battery and the bus, or an alternator, generator, and a bus. They don't let us have this much anymore. That'd be too much. It'd be excessive. That wire would get too hot. So between a power source and a bus, it's 2% max. So if we're running a 28-volt system, 2% would be, I'm going to do the math. I should have done this before the PowerPoint. 0.02 times 28 is half a volt. Half a volt on a 28-volt system. Notice it's much lower than what they're giving you on a chart for running wires through an aircraft. They will phrase this a little tricky sometimes. I've seen before on an FAA question that says on a, what would you call a component that you absolutely need? Somebody help me out. Say what? Not the name of the component, it would be a critical, thank you, critical operating system. Sometimes they'll phrase it, they'll say on a critical operating system, the voltage drop can't be more than 2%. That's like thrown in there once, maybe. Usually the question you'll get is between a power source and the bus, what's the maximum voltage drop? And then the answer is 2%. Your alternator or battery, fairly critical. So it does still fit in that category. If you had a wire going out to something else critical in your wing, they might change it, but usually something out in the wing is not a continuous use critical, so we don't have to use it. But 2% on a power source to a bus might get you with the word critical in there. If you see the word critical, think, well, my alternator's critical and my battery's critical. They're looking for 2%. All right. We are going to take a little break because instead of using all these charts, which would be a huge hassle, we're just going to use that chart. So let's take a break and we'll come back in. We'll do a little bit of math. 9:30. The good news is, towards the end of this class, 15 days from now, mostly.
Is there any significant reason why we know delta?
When we get into alternator control, I will point out that on a Y wound, they will sometimes, and I don't know that you have to know it, but it's interesting to know it. On a Y wound, they'll sometimes take this terminal here, which doesn't show up on our standard. Yup, they'll pull that and they'll supply AC power to it.
So that is an AC power.
Well, this whole thing's AC,
Yeah.
but we run through a diode bridge.
But these are going through diagram. And then delta wound, what's the point of, is that just that?
Well, this one, this still has 3 terminals.
Which one is
It's-
this, Joe?
Yeah, there's an advantage to this. It's if you're leaving an AC
How do you wire it up?
in aircraft, there's not.
What are these?
Yeah. Well, this is still 3-phase. I still have terminal A, B, and C.
Rectifiers?
There's I can't remember exactly what it is. There's
Alright,
it's-
we don't know if this started.
You don't need to know it in aviation. It's a slight, it gets down to, windings here, and here it's only going through one winding. So a delta wound, the windings
Because both of them.
it's something to do with the resistance and then the engineering of how we reject the power. It's really, really deep. Oh, rare one! Yeah.
Oh, no. We have one here.
Yeah.
Those are great cats. I have a picture of that cat just chilling in that egg.
Really?
Okay. Electoral bus is gonna be a review similar to what we had in airframe. So especially if we have the video, but, if you run on buses and power plants, I think we have some videos on it. This one is a little bit trickier because we're dealing with undercurrent relays. I'll have to think through that one, figure out how to either get you the video or.
Probably not that, maybe
I mean, the normal would be to get you the video, right? If you're gone. It might work to catch up. So these two, not this one?
Yeah, just these two.
I would say, just because it's a big review day, try to do a good job where your labs are close to wrapped up here, maybe.
You could.
Let me rephrase it that way, so that you're not planning on doing any labs this day. Kind of go.
Another thing, 175 question. What do you use to clean the windshield?
Oh, sorry, this is
Yeah.
class 175. I'm like,
Complete-
that's not 175. Best is water, once we're not into winter, there should be a spray bottle of water. So spray it down without a ring on your finger, wipe it all off, and then there's a chamois. Chamois is not to take the dirt off.
Chamois is one of those like synthetic wrap.
That's not intended to take the dirt off. It should be water, wash all the dirt off with your hands, but now your windshield's wet. Use the chamois to dry the windshield. There may or may not be a straight hand plexiglass cleaner out there. Using that,
It was pretty dirty yesterday, so we got back.
just water.
And I looked and I couldn't find it.
Okay, so yeah, it'd be like the same as Smash. Basically, they just have a water bottle, and you're wiping the dirt off with your hand with a lot of water. And water left up there, water off. And the reason I explain it that way is if you use the chamois to get the dirt off, A, the chamois gets loaded up with dirt, and B, you're spraying. So lots of water and just light.
Okay. That's how you went to Cincinnati and brought it home really quick.
F-16s flying all over the place.
Yeah.
Yes, yeah.
So it's pretty awesome going to land. But I'm thinking about, I don't, right now the fog sharks. I wish I was like maybe wanting back on Sunday.
Oh.
But I was thinking about flying to Alabama Saturday. So if it doesn't work out, we may try next weekend. But anyway, I want to like do the same thing I did.
Flying what? All right, what Brad says. I thought he said he wasn't real well.
He said 9 days.
Okay.
But I would need to double check.
I don't necessarily have a problem with it. That would be his.
Well, more for running if I was you, for like you in my plan and say, here's some stuff you're missing.
Do you have a calendar?
I never know.
This is still April. It all depends on the weather of the day. I would say in the morning, there's a less than 50%. No, my hair's a mess. DFR here, I'll say 10 in April. So the question's not gonna be, like, say you're planning on coming back, when, but I would say 70% chance that you can come back Wednesday. Oh, this weekend. Oh, sorry. This time of year, but there's a 30% chance. No, you got a 10-day forecast, so I would have to look at the forecast. They're pretty good. I was gonna fly the full point down to Liberty, and, Liberty University is in Virginia. So, I was gonna fly down for this last week, and the weather here, if I would've left, like, Tuesday morning, looked good. Weather at Liberty was good, but I had to look really close. The system was moving through, and when I would've been flying through, it was like, it might be good, but you gotta look at visibility, and it was down to 50 miles. And so the issue was, departure was good, arrival was good, but on the way there, so that's the kind of thing we're going.
You guys fly IFR in that float plane?
I haven't been tested. I've not done that one. I haven't actually flown so far since I've been on it. So,
Y'all can fly.
IMC, not IFR.
Y'all always
Not
flew
IFR.
Y'all are always following Rivers.
Yeah, it's 100. take them away. If you wanna put them in a, what do they call it? Sealable container, you're welcome to do that. I think last time I did that with Hannah, she put them in the kitchen, so at least we didn't throw them away. And I was like, that was nice, actually. I'll do that. Yep. I'm one of those kids that tip stuff over. Ava's missing hers open. I'll use that as a good excuse. I'll be right back. Ooh, it's full. I'll take it. I'll be right back.
Yeah, it'll be good.
We're not supposed, Kurt, we're not supposed to have.
Yeah, thank you. All right, she's sleeping. I hear in her car. All right. So out of courtesy for your fellow students, so we don't waste class time, don't open those in here and make me waste time. Bring them out. That's still not the lunchroom. You want me marked absent? Okay. 2% for generators, alternators, batteries, main line going towards the bus. That's what you gotta remember. Otherwise, you're using that chart. These numbers off the chart are the exact same numbers that show up down here, right? So if you're taking your writtens and you're like, where did that chart go? As a reminder, these numbers down here are the same numbers. They just transferred it from here to here. Now, that said, we have to have either the continuous flow or the intermittent flow. There's two different charts. I went in, Barb can hear me or not. When you take your writtens, they give you the supplement, right? And in the supplement is a chart. I looked at one of the supplements, and I'm gonna check with Barb later and be like, which one do you give out again? Because one of the supplements still has this chart with the 3 curves. It should be gone. It's like, this is old, we've got rid of it, but I think that still might be one of the charts they give you, unfortunately. On my IA, they finally updated, and this is the correct chart. It's the most current. It's what's in AC 4313.1B, I think is the number on the front, right? So this is the current chart. So this is the one I'm gonna review and teach with you, and then we'll go over the other one slightly. So on this, you gotta make sure you get the right one, continuous, and we're just gonna follow it across. So let's do some numbers. The sheet in front of you, you can do it on. And continuous, as a reminder, means is it gonna operate for more than 2 minutes at a time? That's the general rule. So flaps don't go for more than 2 minutes at a time. Gear doesn't go for more than 2 minutes at a time. Landing lights, taxi lights. Yeah.
So, concerning continuous flow operating for more than 2 minutes at a time, or less than 2 minutes at a time, what about the strobe light?
So the strobe light, my understanding is when it's on, it's on. So even though it's blinking, it's on. You turn it on for
But it's
flying at
only
night.
drawing current for like 1 second at a
You
time.
really want to split hairs on a light bulb. When you first turn it on, the amp draw is really, really high until it gets hot. So if anything, it'd be interesting to see how much heat's gonna get rejected from a strobe light wire. It would not surprise me if you have as much or more heat rejected from your intermittent strobe light that's going boom, boom, boom. Because how are you gonna measure your amp draw on your strobe light anyway? It's like it's gonna be all over the place. So strobe light's gonna be considered continuous. Yep. Pitot heat is gonna be considered continuous because when you're using it, you are continuously using it, right? You're using it for more than 2 minutes at a time. Okay, did I give numbers? Okay, we're gonna do 28 volt, 20 foot, 10 amp. So 28 volt, 20 foot long wire, and my component needs, or will draw, 10 amps. So I'll let you guys work on the sheet in front of you. I'll draw it up here, but basically, we start with the voltage is the easiest, 28 volt, 20 foot. And instead of going across, I like to find my amperage and highlight it, so I know which one I'm gonna go hit. That was fun. Doesn't like wiring charts either. So if you highlight it before you go across, it solves a lot of your woes. 20 foot looks like it's in between. I hit my number, I come down, and we're always going to the bigger wire, which is the smaller number, right? So in this case, we would say, hey, I'm between 18 and 16, so I'm gonna pick, I need a 16 AWG for that one. So quick review on just how we do that, and my biggest tip is come over to the line you already highlighted. When you're doing your writtens, they'll give you a clear sheet of paper that you put over the image in your book, because they're like, do not write in this book. So you gotta try to hold it still, and sometimes with that, before you do anything, just take your amperage, draw your line down it, and then come over and start so you know where you're going. So if you're not confident with these charts, practice bunch, that's why I printed that off for you. I had a couple more we were gonna do in here, but you should be confident with those. Sometimes they'll ask the questions a couple different ways, and that's where it gets tricky. So they might say, you've got a, I'm just gonna pick one, you've got a 25-foot wire, and this is actually more practical, typically. You've got a 25-foot wire that is, we'll go with 20 gauge in a, I'm gonna switch it to 12-volt system. How many amps can it carry? So if we do it that way, all of a sudden I go, oh, I can't highlight my amps first because they're asking me which line I intersect at. All you gotta do is work part of it from one side and the other from the other side and see where they intersect. So they're starting out with the 20 AWG. So you can highlight your 20, and then you can start working the other way and say, okay, I'm 12 volts, which is the same as 14. They never really decided if it was when the alternator's on or not. Kind of a weird thing, right? So I'm gonna come down to 12 volts, 25 foot. Ooh, I'm way up here. And I'm gonna see, well, what amp draw does that hit when I come across? Okay, it hits 2 amps. So on that size wire, that system that long, I'd have a maximum of 2 amps if it's a continuous. So they can ask the question a bunch of different ways. The IA test, they have 3 possible questions, and she still says go to the chart and do it. The A&P test, absolutely, you need to be able to basically interpret what did they just ask me and where do I draw my lines to intersect.
This is for DC only, or is it, can it be used for
AC or DC, so if it's RMS, RMS voltage, and they won't say RMS, they'll just say AC, same chart. Yep, so if you're running an airliner with 400 hertz on a 110 volt system, chart still works. Yep. They're not asking anything about resistance here, right? Because we're gonna get into impedance worlds, and so they're not gonna make you do the math and say, how many amps will you have in the circuit? They'll just say, okay, you have a circuit, it's a component, we know it's this many amps, what size wire do you need for it? Yep. And back to, if you're designing the airplane, you're gonna use these charts plus an altitude, plus is it in bundles, plus blah, 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 blah. We're not designing an airplane, we just need to understand the concept, so the FAA has you do this so you understand the concept.
If it's shielded wire, does that change all? Because in theory, it wouldn't dissipate the heat quite as well.
I have never been asked that question. I don't know. I don't know. I've never, I guess the answer is it doesn't matter because nobody's brought that up. I would go back to, if you're designing the system, you might want to look that up. If it's supposed to be a shielded wire, I go back to what wire are we gonna put in? We're gonna check the electrical diagram first. It's gonna tell us exactly what size wire is gonna be in there. Or I'm gonna go to what's in there currently. So, especially with shielded, yeah, good question. this one was the intermittent flow. So just for the fun of it, that last one we did was continuous flow, and we ended up with 16 gauge because we were 10 amp, right? Like that. So if we switch those exact same numbers, 24 volt, it's up here, 20 foot, and 10 amp. If we switch charts and go to our intermittent chart, let's see if it's still 16 gauge wire. My assumption would be intermittent, we're gonna be able to run a smaller wire, right? So 28 down to 20 foot. Notice we're way down here lower on the chart. I like to go 10 amp, so I know which line I'm at. I'm gonna come across, and you'll notice I'm almost hitting down below where I even can. So I'm somewhere around a 20 gauge wire. I don't need 16 anymore. It'd be 20 gauge, a much smaller wire. So our next couple slides are gonna deal with case you're below the amperage. What in the world? If our wires get short enough that the size wire we would use would be very small for the size amperage, the FAA is gonna say, okay, at some point, I'm not gonna let you put a 24 gauge wire in and draw 30 amps on it because it's only 3 inches long. They're not gonna let you do that. You could go to this chart, right, and say, well, I don't have 10 foot of it, I only got 3 inches, and I can drop 2%, 5%. I could do a 30 gauge wire, because it's only, they go, no. We're gonna set some limits on amp draws for you. And we're gonna say, when the wires get short, we're only gonna let you run a certain size wire. And most of that is gonna come off this chart, the circuit breaker chart. So if you absolutely have to have 15 amps, you're gonna have to have at least a 15 amp breaker in that, or fuse. And they'll say, okay, if you need a 15 amp breaker for this component, we're gonna say the smallest wire you can run is a 16 gauge. If you need a 10 amp breaker for this component, and the breaker technically is protecting the wire, not the component, right? That's how the FAA likes to say it. The fuse or the breaker protects the wire, not the component. But if I need 10 amps to run the component, I need at least that size breaker, or it's gonna trip. So, in our previous one, if we have at least 10 amps, they're saying, well, you're never gonna run a wire that's smaller than 18 gauge in a 10 amp system. So when I said, hey, on our intermittent chart, we could get away with about a 20. Well, no, because the FAA comes back with the next chart and says, well, you need a 10 amp circuit breaker, we're gonna have you run at least an 18 gauge. If you look closely at either one of the continuous or intermittent charts, if you compare these, so let's grab 15 amp. 15 amp, the bottom of the line is a little bit to the left of, but basically they're saying 18 gauge, 15 amp, 18 AWG, and this is intermittent. Let's check what the continuous one would be. 15 amp, all the way to the bottom. It's slightly to the left of 18 gauge again, so same number. If I compare that back to this chart, 15 amp, and they're like 16. So the general rule of thumb is don't use the bottom of the line in place of the FAA chart. If you're gonna can't find the chart, whatever, you're usually gonna bump one size up from wherever the bottom of that line ends up at. Back to, remember we got that kind of 20% thing, they like the 20% safety. So, most of the time they're gonna give you this chart. You will get it on either your midterm or your final exam, because if you were picking a wire size, first thing you do is check the charts, and then you're gonna make sure that, hey, we have a big enough breaker for our amp draw, and what's the minimum wire size for that. Quick review. For Job's question, he said strobe light. A light is a lamp. And if we're using a switch, now whether that's the cockpit switch or a relay. A relay is a electronic switch, right? We use electricity to control a much bigger contact switch. We need to derate whatever that contactor switch says it can handle. So let's say I have a switch, and on the side of my switch it says, hey, I'm good for 20 amps. I'm good for 20 amps. And just for the fun of it, we'll say we're running it in a 12-volt system. But if we're on a 12-volt system with a light bulb, well, when that light bulb first powers up, we have a super high inrush of current. It's hard on the contacts. So they're going to take that 20 and they're going to say, well, we got a 5 derating factor. So I'm going to take my 20, divide it by 5, and I'm going to say I can only run a light bulb that draws 4 amps once it's running. Light bulbs are the worst. It's a derating factor of 8 on a 24-volt system. They're pretty bad. I believe the written questions that show up, they'll usually do a motor. So they'll ask you on a motor, and they'll say, okay, you got a switch that's rated for 50 amps, and you got a motor that draws 40 amps. Can you use it? And you'll be like, oh, no, because if you derate either one of those, either by 2 or 3, the switch won't be big enough. So derating factors of the switch itself is a thing. Shane?
Is the derating factor so high for lamps or lights, just because they're so sensitive?
It's the inrush. So when you turn a light bulb on, before that lamp is hot, the resistance of it is very low. There's not much resistance. Once the lamp gets hot, now the resistance is higher. So when you first turn that lamp on, you got a really high inrush of current. So it's not that the light bulb is sensitive, it's that the switch can't handle the inrush current.
So that's for incandescent, what's the derating factor for?
They actually didn't, I've never seen where they specify an LED as being different. Because that's an interesting, I think part of it is LEDs don't take much power. So I think they were like, we don't need a derater for LEDs. But I'm not sure, that's a great question. I've never seen explained that you don't have to derate an LED, but they're like 7 or 8 times less amp draw for the same wattage output. And so yeah, if you're engineering the airplane, that'd be a good question. An inductor, whether that's a relay or a motor, the reason we derate those isn't the inrush, because on an inductor it fights a change, right? On an inductor, the reason they're derated is when we shut that thing off, the collapsing field says, no, I wanted that power, and you get this spike that wants to jump across the contacts as they're opening, and it's very hard on the contacts. So we get contactors that are rated for higher amperages, so that when they're opening up and you get that voltage spike, we don't wear out the contacts as fast. Because theoretically, we're gonna have a little spark every time you open that switch. So we want a big, heavy-duty set of contacts on an inductor so that we just don't wear it out as fast. All right, we're gonna do this one. It's not real good here. I do have the paper copy, but just to review, the chart is very similar, almost identical to what you have on the other one. If you get on your writtens that they give you this, you would do the first part the same. So does this say okay, so intermittent rating is curve 3, continuous is curve 1. So what they do is instead of giving you 2 charts, they had 1. So if we said it was we start off with the other one, was what, 24 volt, 20 foot, 10 amp. So we still would go to the 24 volt, this one's 28. I still go over to my 10 amp and highlight it down. So I know it's a 28 volt down to 20 foot, hit that, and then I'm gonna come down, and it's hard to read on my screen, I know, 16 AWG. So, oh, okay, cool, it's basically the same chart, right? But what they do is as you're dropping down, they'll have you double check, and they'll say, okay, but if you've got 10 amps, you're never allowed to drop below whatever curve you're on. So if you were on the intermittent curve, which is way down here, they're saying we're never gonna let you drop below it. If you were coming across and you hit the curve, you'd say, whoop, that's all the farther I can go. So my continuous curve, number 1, in our case, no problem, we're still 16, not a big deal. But if I were to change my amperage and give you a 20 amp circuit, so this shows up with a little higher amperages. And let's say I'm 20 amps continuous. Continuous intermittent, it's still the same chart on this old one, it's just a step afterwards. So 28 volt, 20 foot. I gotta go to 20 amp now. And come over continuous right there, be about 14 gauge. But the last step we do is we say, okay, last step, let me take my 20. Oops, I hit my continuous curve before I got down to my wire. Once I hit my continuous curve, I say that's all the farther over I can go, and I'd come down and say, well, since I'm continuous, I'm gonna run a little bit bigger wire, 12. So if you don't get that, you wanna talk to me personally or whatnot, this is the old chart. You should never use this, not an AC43 again, but if you get it on writtens, I think they eliminated it on most of them, but I'm gonna go check with Barb later in the day and be like, which supplement do you give them? It's just something about the writtens, all the changes have to be approved. And it's a process, so it's not easy. When I was down at Baker, it was funny. There was a question that was absolutely wrong, written wrong, it's graded wrong, and the FAA won't change it. So we just have to pick the wrong answer. So on this one, the last step is making sure you don't cut through any lines. If you hit a line, oh, it dropped through, and that's where you're at. All right, we're getting close. We got 4 slides left. That's about right. I said 3 hours. We're right in the neighborhood. Insulation materials. We talked about if you're the engineer, the limiting factor on amperage is how high the insulation's rated at, right? And this is why I say engineer, because some of these terms are like, well, at what temperature were they testing that at? Well, if you're gonna print on it 200 Celsius, you better do this test at 200 Celsius, right? But, to continue on, they have some questions on what's the insulation made out of. Nowadays, it's a lot of vinyl, sometimes Teflon. It doesn't necessarily matter. You wouldn't make an insulation out of any metals, right? You're not gonna, I don't know, it's just a silly question. They might give you a list to say what could insulators be made out of. Glass? Well, probably not a wire insulation, but glass is an insulator. So then they're gonna say, okay, we got a couple terms for you. Insulation resistance. So when you see the word resistance, you should be thinking, oh, I can measure that with an ohm meter, right? So that's resistance to electricity passing through, and you test it with a sensitive ohm meter or a megohm meter, because mega ohms are really big. So sometimes they're called a megger. Usually, if we're using a megger to check resistance, it's not a wire running through your aircraft. It's going to be like a winding on a alternator or a starter motor, and you might check the resistance from that winding to ground with a megger. But insulation resistance is how many ohms of resistance do I get in the insulation. They will also bring up a term called dielectric strength. So dielectric, remember, is separating, like in capacitors, separating the two things. To test dielectric strength, you're asking how much voltage, how much pressure can I put across that insulation before it breaks down and we get some amp draw going through it. The main thing with this one is if you were testing dielectric strength, basically you're testing until failure, right? Because if you put so much voltage to the insulation that now we're jumping amp draw through it, we're gonna leave carbon trails behind, we've ruined that wire. So if you have them come up with a dielectric strength term when they're talking about wires or insulation, you're like, okay, they're just giving me that info so I know stuff about electricity and wiring. But to test the dielectric strength, you are going to ruin the wire. That's something the factory would either give you or list. Hey, what's the dielectric strength of that insulation? That's how much can it say, you shall not pass before we have breakdown. Where resistance, they're just saying, oh, how well, and although they seem like the same thing, they can test two different things, but we're at an engineering level that we're not gonna deal with. That said, the reason I bring it up is if we had a wire, I'm gonna draw myself, we're gonna pretend the black is copper, we're gonna pretend the green, as a cutaway view, the green is the insulation on the outside of our wire, okay? When is that wire insulation bad? Say I got an airplane and all of a sudden I got a cut in here. How do I know if I need to replace the wire or not? Is there a way I could test it? This is just brainstorming. This isn't a right or wrong answer. Kind of a weird question, isn't it? Shane?
So you would know what type of voltage drop you're allowed to have, but if you have more than that?
Through the insulation itself, though?
No.
So that's not working well. Matthew?
I'm thinking something about checking the resistance of the remaining insulation. I don't know how you figure out what you need.
Yeah, it's pretty, you want to take a guess or a thought? So basically, we can't check it. You could potentially say we could double check the dielectric strength. If we're using a mega ohm meter, it gets a little weird because you're like, what, am I gonna put the mega ohm meter here and then on the wire? So the answer to this is if your insulation is damaged, your wire is damaged. You need to put a new wire in. So as weird of a question as that is, I try to get you guys to kind of think through, there's no way to test that without causing it to fail. And then once it fails, well, now it's bad. So basically that's why the FAA kind of talks a little bit about dielectric strength versus insulation resistance it's to get you down that path to say if your insulation is cracked, cut, what's the word you'd use if you abraded it? See,
Abraded?
if it's abraded, if it's worn, it's bad. It's bad. So you got to replace it.
How many wraps of electrical tape to restore it?
Exactly. That's what all the heating guys say. We don't. So now that said, we're gonna come across some stuff this afternoon on individual wires where they say, don't do it, but if you do it, don't do it, but if you do it. So there would be some potential questions on what's the insulation rating of heat shrink. Remember we had those handshakes? But that would, in my opinion, that would fall in the don't do it. But if you do it, you might, so that's an interesting question. But yeah, the FAA and the answers are if the insulation is damaged, the insulation is damaged, which means your wire is damaged. So they don't really give you any room on that. Their insulation is there for a reason. If they didn't want it to be at the rating of what it is, they wouldn't put insulation on the wire. And they don't put extra on because there's weight in insulation. So if it's damaged, it's damaged, and you got to replace it. All right, a quick review. I think I threw this in today. We deal with it a little bit later, I think. Should be all review from airframe, but some questions on state of charge versus load meter. State of charge is going to be an amp meter that's connected to our battery, the line from the battery, and it can go positive if we're charging our battery, or it can go negative if we're discharging our battery. So it's telling us, when we say state of charge, it's telling us are we charging or not charging. That's where the charge word comes from for state of charge. Our load meter, on the other hand, is telling us how much load is on my either alternator or generator, my electric producing device. So we might have, where we're flying the airplane, where my state of charge, if I have both of them, is at 0 because the battery is charged up, it doesn't need any more voltage. It's like, you're not charging me, but you're still using 30 amps out of your alternator, and the system's running on 30 amps. So this picture here could be a point in time, right? So the load meter is how much load is on the voltage producing device connected to your engine, where your state of charge is on from the battery. So back to that 80% rule in AC 43, if you turn all of your continuous load systems on your aircraft, and I think they like the radio as well, they don't want you to be over 80% of what your alternator and or generator can output. If you get over 80%, now we're dealing with that, well, if it's over 80, now we gotta have a load meter so that we know where we're at, and a placard to tell the pilot, hey, you gotta watch your load meter, because you can turn the load past 100%, and you don't ever wanna be past 100% on there. Now, if you have some intermittent load that would bump it past, we're like, the battery will handle that. So that's why the continuous loads are the important one to kind of be aware of. If the continuous loads will be more than 80%, they say, well, then we better have a load meter and we have a placard to watch it.
If you have a state of charge meter and you are over 80%, do you still need a load meter?
If you have a state of charge without a load meter, you will never be past 80% because you will have installed components in your aircraft illegally. So anytime you can get past 80, anytime somebody's adding a component to that aircraft that would push it past 80, they're gonna add a load meter and a placard. Or they're gonna put a bigger alternator in so that you're not past 80 again.
How often do you as a pilot actually have to watch that and get past the?
Small aircraft, no. As you get bigger and bigger, you got more stuff you can turn on. So I have never officially flown an aircraft that I have to watch it. Normally they just put a big enough alternator in to handle it.
The 80% that's
Continuous. Yep, yeah, so landing gear doesn't count. Taxi, landing lights, debatable. Debatable. Alright, so this picture here, we've got, where's my battery, Marcy? Here's my battery. I like the square ones, they're easier to find. I get it. There's my battery. So my battery comes over to my master solenoid, through my master, up to my bus, and we're at the bus. I should have had an amp meter. Here's an amp meter. I've got an amp meter that is basically between my bus and an alternator. So my amp meter, it says amp meter, you have to believe me, I can see AMM. My amp meter is between my alternator and my bus. So in this case, is that amp meter, is it a load meter or a state of charge? Load meter. So this amp meter is a load meter. So just be careful, they'll move those words around on you. Every state of charge is an amp meter, every load meter is an amp meter, but we use load meter from an alternator generator, we use state of charge from the battery of the bus. One more picture. Ooh, this one's hard to see. There's my amp meter. Here's an alternator. So there we go, alternator, amp meter, battery. Oh, this one doesn't give us a bus, it just says the back of the master, and it starts going to all kinds of components. So that's the Cherokee Arrow. Cherokee Arrow? That's the Arrow, and once again we got a load meter. Do I have another amp meter in there? Where's my battery?
That amp meter is in series?
Amp meters are always going to be in series because amps measure it. Now, if they have a shunt, amp meter shunt, the voltage will go through the shunt, and then the amp meter's technically a voltmeter at that point, right? But it's in parallel with your shunt.
Right.
So what's the amp meter? I would consider the shunt part of the amp meter at that point. So yeah, always in series. Okay, I think there was supposed to be a second amp meter in here, but I don't know if I can find it. Where's my battery? Does anybody see a battery? Voltage regulator, alternator, master. Come on, battery. Battery master. Here's my battery. All right, battery through my battery master. Nope, they don't give it to me. Must have been a different drawing. I had a different drawing that had two of them. All right, here's a Cessna 206. battery contactor, and my ammeter between my battery contactor and my bus bar. So which one is that on the 206? Is that a load meter or a state of charge? State of charge on the 206. Now, somebody might add an additional one. There might be an STC. But yeah, the 206s I have flown don't have a load meter. I have no idea what my alternator is putting out. No idea. Which is a weird thing. So all I know is, am I charging my battery or am I not charging my battery, and by how many amps? So that's a typical 206 there, no load meter.
The load meter would be between the bus bar and the
Yep.
alternator?
If you had a load meter on this 206, it would be right there. You could put amps on there, but it would be a load meter. So now it's between my alternator and my bus bar. Yep. Cool? Alright, so that's a little bit of review, but I bet if we didn't do that, by the time we get to the end of the year, some of you guys would be like, ah. Okay, review for safety. We have that box that has these lockout takeouts right by the tool room, right? So if we're doing electrical stuff and we take some wires off and they're dangling around in an aircraft, we should put this on with a tag. It'd be great to have a sheet of paper that says the work in use, so that we know we disconnected wires. You guys took the whole wings off. Were you good in mechanics? You got what, good, yeah? Did you use these? Bad. Shame on you all. Shame on you all. Because how do you know which wires you gotta reconnect? Maybe you made a list. What battery gets turned on? So anyway, it's Ryan's class. He's having you pack them up, but more a thing if you have one circuit or two circuits, right? You put that on there. We put these on the landing gear of the 206. If it's going to sit for a long time, we'll pull the circuit breaker for the landing gear pump or relays, and we'll put them on so nobody accidentally puts the landing gear up while it's sitting on the ground. But while you guys are replacing wires for my class, if you disconnect a wire from somewhere, we don't want to accidentally turn that wire on, have it sparking around somewhere it's disconnected. So go ahead and do a lockout tag out on that one. Now, P-leads don't carry electricity. I know we didn't cover starting systems yet, so I get it. But so there's no circuit breaker for the P-leads, right? Well, the P-lead does what if we do not want the magneto to run? Does anybody know that one yet? I know I haven't taught it yet. It grounds the magneto. You guys had it on your mock-up boards, right? If I don't want the thing to spark, it grounds it. So if I remove a wire that grounds it to shut it off, what did I just do? I turned it on. I turned that magneto on. If somebody turns the prop, that magneto is live. It will spark now. So if there happens to be fuel in the engine, kapow, and the prop's going to hurt somebody. So if you take a P-lead off, you can't put one of these on. It does not work. It doesn't matter if the key is off. The P-lead's removed, that magneto will fire. So put a jumper wire from the P-lead to ground somewhere. So anytime you have a P-lead off, as soon as you take the wire off the P-lead, make sure you got a jumper wire from that P-lead to ground somewhere so that it's safe. And I would also recommend putting on that work in continuous work. What's the name of that sheet?
Work in progress?
Work in progress. That's not what I wrote, but yes. Maybe it is. Maybe that's what it is. Work in progress. I think you're right. So make sure you're putting jumper wires between magneto, P-lead terminals, and ground so that those magnetos aren't hot while your P-lead is off the aircraft. Does that make sense, Israel?
If we're working, not talking about magnetos, but if we're working on electrical systems, wouldn't we just disconnect the battery anyway, so you can't run anything?
That would be a good, so like when you have the wings off. Yeah, so if the wings are off, if you disconnected the battery, yeah.
So even if we're doing like general electrical, you don't really want the batteries hooked up anyways.
Depends how you look at it. It's an awful big hassle to disconnect that battery. Often. You guys have it easy because it's SMAT and the panels are all off. A lot of times you're taking panels out of fuselages and crawling in the back. And remember that lab we had where I had you inspect the battery box? On the ones that were complete, that was a lot of work. And you got to torque it back on when you're, yeah. Normally, you would just leave the master off and if you're doing a tremendous amount of electrical work, you might take it off. If you're working on the starter or the master solenoid, yeah, disconnect the battery. But I did a avionics switch in the 206. I'm not gonna go disconnect the battery to the avionics switch. I'm just gonna make sure the master stays off.
Most of the things that we're working on, the ignition leads are off, he's throwing the ground fuse. The ignition leads are off.
Yeah, okay, so the spark plug wires being the ignition lead, say you got all your spark plug wires off, the way I'm gonna phrase that, if you disconnect the P lead, just put a jumper on. I mean, alligator clip jumper, it's super easy. I get what you're saying, oh, I don't have any spark plugs in here. I'm like, well, how hard was it to just put a jumper on there?
We're actually replacing the wire.
Yeah, it's just one more, it's kinda like walking around with a gun. The really highly trained guys will say, well, the safety's on. I'm like, well, still get your finger off the trigger. Keep your finger outside the trigger guard. Okay, oops. I think that is it. So I say head to lab time.
That is it right there at the end.
Wow, look at that.
Hanger.
You guys got what, about an hour? About an hour, there's a bunch of paper labs. You could jump on whatever lab number that was where you need to make up the master relay. You should have work to do. You could, hey, where did the sheet with the wires go? Did it make it to the back? It's on the wall. Perfect, somebody already walled it for me. You could go find your wires and start putting your names on those. You could start disconnecting those wires if you want. I'm gonna go talk to Ryan here for my 10-minute break, which isn't much of a break, to be like, what's going on? So, okay, dismissed. We made it through the hard part. Not bad for a Monday. It's for me. Isn't it Monday today?
It's Monday and Friday.
This is Monday. Yeah, I told Nick, I was like, hey, just so you know, tomorrow, I'm not gonna be here till 10, because I gotta meet with the FAA. Meet with the FAA on Saturday? Like,
Did they buy you breakfast? No, on Monday.
like, no, it's not even Monday today.
It's Monday and Friday.
It's Monday, yeah, I